Hello everyone and a warm welcome back to my channel. I'm Emerson Aposkuri and I'm thrilled to have you join me today as we continue our journey through the captivating realm of artificial intelligence and machine learning, especially natural language processing. If you're new here, consider hitting that subscribe button so you don't miss out any of the exciting content we are diving into. Also, I suggest you to check out my previous videos, although I know they're not a lot, but if you like them, you can support me by liking and commenting on the videos, and if there was any question, absolutely I will check the comments and answer you. Trust me, you won't want to miss what's coming up. There is much to learn and explore in ever evolving world of technology. And before we dive into today's interviewing topic, I wanted to thank you a lot for amazing support that you've done on my previous videos. Your comments, likes, and somehow sharing inspire me to keep bringing up you valuable insights into the latest advancements in machine learning technologies. Um, Now, if you're here with us from the start, you might remember the series that we had on transformers, and we talked about the topics like self-attention, positional encoding, the embeddings, and the implementation of transformer architecture in both TensorFlow and PyTorch. If you haven't had the chance to explore those videos yet, there will be a link on the top of this video. I suggest you to watch them first, especially the first one, which we are talking about the main idea of transformer architecture, and then come back to this video, which we are going to answer some of the questions that may come up into your mind about the transformer architecture. Also, if you're familiar with transformers, there is no need to watch that video, although I suggest you, but there is no need, and you can watch this video. If there was any question, you can ask the comments, or first watch that video and then come back to this video. Maybe some of your questions are already answered. In today's video, as I said, we are taking a step back from hands-on implementation to answer some of the burning questions that often arise when working with transformers or reading about them. Um, have you ever pondered the concept of the right shift during decoding? I know in the series uh, we didn't talk about the shifted right in here, but in this video we are going to talk about that. Also, we are going to talk about the encoder-only and decoder-only models. What do they exactly mean? Because you know. Um, Okay, we know that we are just going to use the encoder part of the transformer architecture like here, or the decoder part, but the question that may come into your mind is that, so after connecting the encoders together, what happens? Or after connecting the decoders, what happens? Or whether what are the inputs, or what are the outputs? And the one of the main questions that may come into your mind is that when exactly we use the decoder only, and when we use the uh, you know the decoder only models. So first, let's talk about the right shifting in here. What does that uh, mean in here when we're talking about the right shifting? So in a transformer model, the both encoder and uh, decoder operate on entire sequences simultaneously. As we talked about, that was the advantage over the recurrent neural networks, that they were, you know, uh, doing that one step at a time, and that had some problems like gradient vanishing, or the long time to train the model. Uh, but transformers were doing that with adding the self-attention mechanism and positional encoding of some of those things. Uh, so we had an encoder. The encoder processes the entire input sequence simultaneously and generates a representation of the input. Each position in the input sequence is processed in parallel. So we are not just uh, checking the words one by one, um, and we are having all of them together. Uh, In the decoder, however, that we are saying that we have shifted right, that I will talk about that in a second. But during decoding, the model generates the output sequence step by step. At each step, the model generates a single token based on the previously generated tokens and the encoded representation from encoder. As you can see, we are getting that in here. So we are getting some kind of output that is the previously generated tokens and the encoded representation of the encoder. So that's what exactly the encoder decoder model means. When we are encoding all the information in the input sequence, and then we are going to generate the output sequence. By the way, when I say sequence, I do not mean the sequence of words. It can be a sequence of numbers. That means it can be used for videos. It can be used for images or something like that. Although you should do some adaptations and something like that, but the sequence does not mean just a sequence of words. So we are passing the encoded representation of the input sequence, which can be everything other, including a sequence of words and the previously generated words. And then we are using those information to generate another new word. But now, what does that shifted right means? The shifted right concepts, it's exactly that we are generating some tokens and then we are using the previous ones to generate a new one. So that's shifting right. That's what it exactly means here. We are, I mean, during the training we have both the input sequence and the answer. For example, and the output sequence. For example, if we have question answering data set, we have a sequence of words for the question, a sequence of words for the answer, and we have both of them, but we are not showing the future to the embedding. Also, we are not using the exact words in the output. We are using the generated words by the model, generated words by the decoder to generate that. For example, consider that we are doing a translation. We have three words, A, B, and C. Let me do that in Paint for you. Okay, let's give you an example. Consider, for example, we have two sentences. Let me type that for you. For example, we are doing a translation task. Okay, from English to Spanish. So we are doing a translation task. Um, from English to Spanish. So the input sequence for us is, for example, you are mine, and the output sequence would be to eres mia, if I'm not wrong. So we are doing something like that. Now, as we are talking about the input and the output sequence, what happens is something like that. For example, you have your encoder. Your input is encoded to something. So when I say English in here, I mean the English input. So we gave our decoder the information that we had as our input, and then we have encoded thing. So when I put these braces in here, I mean the encoded English text, and then we are giving it to our decoder. So decoder, and there are I think 3 or 4 steps in here. The first step is that we are giving that encoded English text and also the start token or something like that. It may be different based on the language model that you use, but just consider that we have a start token. We are giving that a start token in here, and we ask the decoder to generate a new word for us. For example, as it is trained, it generates for us 2. In the second step, we are giving our decoder the encoded English text as well as the start token and 2. By the way, we're passing the embeddings and all those information, um, but the shifting right exactly means something like this, because we are adding 2 here. We are adding something to the right that they call it right shifting. And then we ask the decoder to generate the next word for us, which will be rs, and then we do the last part, something like that, and then we get Mia, and then we get the end token or something like that, and that's completed. We have the Spanish text for us. So that's how the translation works in encoder decoder model, a transformer, basic transform model that has both encoders and decoders. And yeah, the shifted right, as I said, if I want to conclude everything that I said, the shift right input in the decoder means that at each time step, the model uses the token that were generated in previous steps as input instead of using actual target tokens. This helps the model learn to generate sequences in a sequential manner, and considering the context of um, you know uh, previously generated tokens. In summary, while the transformer processes positions in parallel within each time step uh, of the encoder and decoder. And the shifted right mechanism in the decoder ensures that the model generates tokens step by step, capturing the sequential nature of the output sequence. So that's it. That's very simple. Okay, so yeah, that's exactly what happens in uh, encoder decoder on the models and everything in there. So let's go back to what we were saying. So we answered one of the questions, which was about this shifted right thing. Uh, the other questions that may come into your mind, I don't know, it's a very common question. Uh, but when I started studying transformers, I had these questions in my mind. That what happens when we increase the number of tokens in a model, that this information will be used in our future videos, but and that's a weakness of transformer model. When we increase the number of tokens, input tokens, so we can say that there is no change in the size of the layers in feed-forward networks for us, because that's kind of hyperparameter. It does not depend on anything. But the size of self-attention changes, because as you can remember, we had a kind of matrix for that, which have t tokens in here and t tokens in here, and we were calculating you know uh, the tension between two tokens, for example, token 1 and token n, um, and putting that information here. Oh, if we have causal uh, thing, it was upper triangle matrix or lower triangle matrix. Well, I'm not talking about that specifically. Just I want to remind you that we had the matrix for self uh, you know and self attention. So now that we are doing a multiplication in number of our tokens, for example, we are using twice tokens that we were using previously. uh, what happens in here, that the size of the matrix increases by 4. So that means the computation here will be more expensive for us, and that's not what we want. So that's a problem with transformers. I just wanted to say that what happens if we change the number of tokens. Also, there's no change in the feed-forward neural networks. Otherwise, we're changing then the size of the matrix. That absolutely has some effect on the computation power of transformers. Um, yeah, that's another question. Um, I think now we, we can talk about the encoder and decoder only models, or talking about some kind of transform models out there. We have lots of encoder decoder based models that are trained with some type of objective training or pre-training objective like T5. T5 is encoder decoder model that has you know all of the information it needs, and it is very great model for generating sequences based on the input sequences, like translation or consider question answering or everything like that. But nowadays, as you may be like I can say, you absolutely heard of the Chat GPT. The GPT models are just using the decoder, and they are generative models, not they're not encoding information. Also, we have BERT, which is very famous, and that uses only the encoder of transformers. So how does exactly they work? Let's talk about that. First, let's start with BERT. BERT, or pre-training of deep bidirectional transformers for language understanding. Although it has some kind of new idea of using bidirectional transformers, but the main thing in here is that they are using just the encoders of transformers. And we are going to, check what happens when we are just using the encoder of the transformers. I'm not going to, talk about this paper a lot because I suggest you to read it. It's not about what exactly we are talking about in here. It's just an example, kind of. And yeah, we are going to talk about what happens when we use some of those things. For example, consider that we have some position embeddings. We are doing token embeddings, segment embeddings, and uh, based on the input that we have, and then we have some kind of embedding. We are not talking about these informations that are in BERT language model, but I think there might be a picture about, yeah, I wanted this. So this is a picture that we can see, although comparing it with Elmo is not something that we want in here, because we haven't talked about LSTMs or RNNs, which I have in my mind to create some videos about RNNs and LSTMs in the future videos, and then we can talk about Elmo and this picture more in kind of short video. But now let's focus just on OpenAI GPT first in here. So as you can see, we have some kind of embedding or coding in here. I can say embedding because it has some information from the words, maybe some information from the uh, position of that word in the sentence and something like that. And then we have some transformer parts, and they are connected to each other, and then we are getting the output. But in BERT, we are using this bidirectional. So we now know what that bidirectional means. The transformers not only are or the transformers or maybe transformer parts are not just only connected to each other, but like what happens exactly in the left to right, but they are connected to each other right to left as well. So the question that may come into your mind, why this does not make any problem for BERT? What happens if we do this with GPT? Because and I can say we have GPT-4, which is the fourth version of GPT model, but although they had made lots of changes, but they didn't make any change regarding using the bidirectional thing, and that is why we should know how encoder-only and decoder-only models works. Because using bidirectional thing in decoder-only thing that we're generating sequences based on nothing somehow, um, is a very important thing. And I'm using bidirectional thing that does not mean that much in there, and it's biases the model cannot generate good things, good words in the final product and something like that. So let's talk about um, the encoder only and decoder only model. So here we are just talking about encoder only models. An encoder only model is a variant of the transformer architecture that includes only the encoder component without the decoder. It's designed to encode the input sequences in a fixed dimensional representation, which can then be used for various downstream tasks such as text classification, sentiment analysis, or language models. So, as you can understand in here, what we're saying is they can be used for what? They can be used for classification, sentiment analysis, I don't know, emotion recognition, emotion classification, language modeling, which may be somehow, weird for you because we talked about encoders and we said that it just encodes the information, but I will talk about that as well. And we are saying that you know the decoder-only models are typically used for classification models, and the reason is the architecture of them. So the decoder-only model, the process in them is as follows. First, we have input encoding. The input sequence is tokenized and embedded just like in a standard transformer model. So we are not changing that thing at all. We are just using we're doing the input encoding, but like what we had. Uh, Input encoding means input embedding and positional encoding together. Then we have encoder processing, which is the exact encoder part of the transformer. The embeddings are passed through multiple encoder layers, uh, which, if you remember, was 6 in the Attention is All You Need by Wasawani paper. And each of these layers, each consisting of self-attention and feed-forward neural network sublayers. We had feed-forwards and self-attention. I also add addition and normalization just for uh, saving the information from the past, also for a lot of stuff that we talked about in the previous videos. So yeah, that's what happens in encoder processing. The self-attention mechanism captures contextual information and relationship between tokens, and the feed-forward layer processes information further. So they are getting some contextual information, and then they are processing to reach to some new information. And the third part of the processing encoder-only model is the output, which the final output of the encoder is a representation of the input sequence. So you are getting the idea. We are just using encoders to to encode the information that we get from corpus. And that makes us to reach some kind of, embedding. We are creating some embeddings from words. We are creating some embeddings from the sentence. Even we have some papers I suggest you to read about them, which are embedding your using. Yeah, they are just uh, generating some vectors for you that represent the whole sentence. Although you are losing some information in there, but you're using them. Also, we have seen that you're using BERT model to uh, have some embeddings of the words. They are called contextual word embeddings. Uh, Unlike the word to wake and all of those things, that each word has a specific and constant uh, vector for itself. Here, because we are encoding the information and we are using the contextual information that comes from the self-attention, we have a contextual embedding for each word. So, uh, this representation that we got from here can be used as a future vector for or maybe vectors for downstream tasks. For example, consider that we encoded all of the information in a sentence. Using that contextual information that we get from self-attention, and that now that we have a vector, we can give it to another simple feed-forward neural network and ask that to classify it for us, and we are absolutely familiar with that task, which we are just adding classifier at the end, and then we feed that vector into that neural network, and then using softmax or anything to just picking up the highest probability, we can say what is the sentiments of the that sentence. But as I said, we had a usage for encoder-only models like BERT, and that was their they're kind of a language model. They can be used for predicting the next word, and that's not a big thing. Consider that we have the whole vocabulary of a language, so we know what are the words in that language. Now it can be seen as a classification task. So what we're doing is just encoding the information that we had previously and then ask a model to find the next word by kind of a classification task, choosing one word from all of those words. So it's a classification task. So it can be used for all of the text classification things. It can be used for I don't know, the sentiment analysis, and also it can be used for language modeling, which is very important, and that makes it kind of available for generating some text, although it takes more time somehow, but it can be used in some way. So yeah, that's exactly what happens in here. But as I said, although they can be used for generating things, but as we are somehow including the information and we are doing this over and over again, the output might not be that much interesting for us. So basically we are using BERT-based models or encoder-only models for classification kind of tasks. So let's now talk about the decoder-only models that they are using here. So first of all, as I said, there is a difference between them, but how they're connecting these things, connecting encoders and encoders to each other is not a big deal. We talked about that in the previous videos, especially in the series that we had about transformers. But yeah, now we're saying that the question that may come up into your mind, that is this softmax and linear layers for the decoder or encoder? The answer is no, it's not for none of them, but it can be seen as decoder. It's not part of a decoder, meaning that when we are using multiple decoders, we do not have multiple softmax, but we have softmax and linear at the end of all of those decoders. So it's part of a decoder somehow. But we are not using them for encoder. As I said, we are using the representation that is made out of the encoder layer, and then we are passing that information to another model that can be simple to find out the class of that sentence, or doing language modeling or everything that we want. So the softmax and a linear and feed-forward network and everything like that are not part of that encoder-only model. So let's focus now on decoder-only model. A decoder-only model is another variant of transformer architecture that includes only the decoder component without the encoder. It is designed for a task where autoregressive generation or sequence-to-sequence mapping is required. So remember this, sequence-to-sequence mapping, and also autoregressive generation. The process in a decoder-only model is as follows. First, we have the input. The initial input to the decoder is a special start token or a seed token to kickstart the generation process. What do you mean by seed token? Consider ChatGPT. What happens in ChatGPT? Just consider two messages that is, you are giving a prompt to ChatGPT and then it gives you an answer. Or consider, better say, not consider ChatGPT, consider, the GPT-3 model that can be accessed via the API that it created. You create a prompt, you create a text, and then the model continues it. How does that happen? That's the seed token. That's all of the information in the token, or multiple tokens maybe. But that's a start for the model. Or it can start from nothing. It can start from a start token. In the second part, we have decoder processing, which is the exact decoder part in here. The input token through multiple decoder layers, each containing self-attention and feed-forward neural network sublayers. At each step, the decoder generates a token based on the previous tokens it has generated and the context it has from the decoder layers. However, this is very important. We are, as you can see in here, which is the full transformer architecture, we are passing some information in here, and then we are doing the multi-head attention. So we can say we do not need to use the thing in here. Okay, we do not need to use this kind of information because we do not have that input. But we do not have any encoding with it. So that is removed. And the final part is the autoregressive generation. The generated token is added to the sequence and the process is repeated what? In different iterations, multiple iterations. So that's exactly what happens in there. When we are talking about the translation task, we added 2 and then created errors. And then we use 2 and errors to generate Mia. Okay? This happens in the transformers. We are doing that in here. We are doing the shifted right thing in here as well. Decoder-only models are commonly used for tasks like language modeling, text generation, and autoregressive sequence generation tasks like machine translation or image captioning. You may ask, how does the machine translation happens in here? It seems like we should have encoder and decoder, but does not. As I said, and that in models like GPT-3, we are giving an input and we ask the model to continue it, like what happens in language modeling. Okay, so how does that happen? We can do that. We can do something like that with machine translation. How? Let's talk about it in this whiteboard again. Let me clean these things up. So we have to give our model a prompt and then it will generate for us. For example, consider we have GPT-3 and then it will generate the text blah 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 for us. What should we give? We can train the model in a way that we are giving it this. We have a token special for English language. We're saying that's English, and you are mine. And then we use a Spanish token and we do not give it anything. And the model tries to translate it to Spanish. How does it know what is this token and what is this token? It happens in the pre-training step. We give it lots of training values to it, or in the fine-tuning maybe also. We are giving it lots of information, and the model tries to reach higher accuracy, higher blue score, everything that's out there. Okay, so it tries to decrease its loss. It tries to increase its accuracy. It tries to increase its perplexity. It tries to increase its blue score, everything like that. Every metric that you have. Okay, so that's what happens GPT-3. I think you got my idea. If it was not clear, please just say in the comments and I will answer you for sure. So that's it. That's it all. So we talked about the encoder and decoder-only models. Let's say this. This is what happens in decoder-only models. As I said, we are removing that part which is uh, using the information from the encoder part. We have mass multi-head attention, we had add and normalization, input embedding, and the input is in here, we call it prompt. Okay, you may ask why we're not saying this output because there is no input and output here. The input and output was for encoder and decoder. We just have an input in here. We are trying to use iterations to generate words one after each other. So we use all of this information to encode it, and then we use softmax and linear to predict the next token. Okay, and as we have next token, we add this with writing shift write it, or shift writing. It doesn't matter. We add that, and then we do this again until we have all of the information that we need. And that's what happens in the decoding only models. I suggest you to read this paper. Also, I suggest you to read the papers that are related to GPT-3 and the GPT-4 and GPT-2. Although the information in those papers are just kind of just reporting how the business works and something like that. They're suggesting to buy their products. They're not giving you the information how they train their model, but reading these papers absolutely let help you to understand what happens in these models. I think there's an image in here. Yeah, as you can see in here, we had text and position embed. We have 12 layers of this. What is this? This is uh, this is exactly the uh, decoder part of the model. You may ask why we just have one masked multi self attention, and as I talked about it, because we do not have any information from encoding to calculate another attention in here based on our output and based on our input encoded input. We do not need to have that. We can just omit that. So they can kind of say that the encoder and decoder in encoder only and decoder only models are kind of sharing the same architecture. Okay, so here also you can see how this information works. For example, when we're talking about the classification, we use start token, then we have the text, and then we have extract token, and we give it to the transformer and the linear model, and then we can get what we want. In the multiple choice, there is another approach. Okay, so what I mean, we have another approach. We have the start, context, the limiter, the answer, and the extract. Extract means that's the end of the sentence. It's, the end token, something like that. And then we are using transform to encode those information and then linear layers to predict the right answer. This similarity is kinda like the machine translation that I talked about. Entailment, something like that. And we have all of this information in all of these papers. There is nothing special about the GPT paper, but about the BERT paper, I suggest you to read it carefully because it talks about how it can be used for different models. You can learn about the CLS token, which lets the model know that we are going to use this for classification. So CLS means classification. It lets the model that we are going to use that encoded information to classify our sentence. For example, for sentiment classification or emotion classification, everything like that. So that was it all about this video. Another question that might come into our mind, I think I talked about it in the transformer videos, but let's talk about that in here. As I said about the lengths of the token, lengths of the sentence, how many tokens we are giving it to model, you should know that there is a max number of tokens that a special model, it depends on the model. We are not talking about just transformers. Transformer is an architecture. It's not a pre-trained model. We are talking about the pre-trained models, BERT, GPT, I don't know, Yama, all of those things. They accept a special number of tokens. You may ask how, ChatGPT works. It has some kind of a memory. It uses the previous information somehow, encoded previous information, and then adds that new information and then generates something. So by encoding, it somehow handles the number of tokens it has. I'm not going to talk about those kind of things, at least not in this video. But that's exactly what happens in these kind of videos. Okay? We're just going to talk about uh, the questions. In the future videos, we can talk about, um, you know, those special things in there. There's a max number of tokens that these models accept. So what does that mean? For example, we are creating a pre-trained language model, and we are saying that it just accepts um, 10 tokens at max. Okay, so we can use other approaches to process more information in there. We can process 20 tokens, but what happens in the model is uh, this: when we are saying that it only accepts 10 tokens, if it is more than 10 tokens, the other tokens are omitted or used for the future. Okay, what does that mean? It means that, for example, consider that we have 20 tokens. The first 10 tokens are processed, then we are using the second 10. Okay, we cannot use all of them there. Or maybe the second 10 is omitted completely. But if it's less than 10 tokens, which the model accepts, we are using some special tokens in there. For example, pad token in there. Pad token, which is something like this, shows that there is no word in there. The sentence is completed. Okay? It is just for giving the model what it expects. And that's it all. I think I answered nearly 4 or 5 questions. We talked about encoder-only models, we talked about the decoder-only models, and we talked about the shifted right thing in these models. We talked about the effect of number of tokens on the computation power and the layer size of feed-forward networks in here, and the usage of different encoder and decoder only models. So that's it all. There you have it. My fellow learners and explorers, we delve into the world of transformers, unraveling the mysteries of right shift, encoder only, and decoder only models, all these things. If you enjoyed the deep dive into inner workings of transformers and decoders, and encoder only and decoder only models, we talked about BERT and GPT a little bit. Um, don't forget to give this video a thumb up, uh, and like it. That would be very helpful for me, and I appreciate your help. Also, if there was any question, please write it down in the comments. If you're new here and want to continue this exciting journey with me, remember to hit that subscribe button and turn on the notifications to you know know when I publish another new video. By subscribing, you'll not only stay updated on the latest insights and breakthroughs, uh, but also become a part of our vibrant community of learners. If you're eager to explore more about transformers and other fascinating machine learning topics, be sure to check out our series of videos on the channel. Each video is crafted with care to provide you with a comprehensive understanding of complex concepts in the world of AI. Also, they are very important nowadays with the introduction of large language models, ChatGPT, and other stuff. I want to express my sincere appreciation for your time and support. Your engagement fuels my passion for creating educational content that empowers you to stay at the forefront of the technological advancements. As we wrap up this video, remember that the journey of discovery never ends. Keep seeking knowledge, experimenting, and pushing boundaries. The future of technologies holds limitless possibilities, and together we are poised to embrace them. Thank you once again for joining me today. Until next time, keep learning, keep exploring, and keep igniting the curiosity. This is Emre Sabasui signing off. Stay curious and stay inspired. Goodbye.